Breaking math news. We have a new way to multiply 4x4 matrices. A new way to fit hexagons in a hexagon. A new way to put circles in a square, and a brand new arrangement of objects in 11 dimensions. Okay, we'll show you later. Just discovered, and many more maths breakthroughs, all announced simultaneously today while I'm on vacation again. So last year I was on vacation when the new biggest prime number was revealed. You can see that was me then. And the next time I go on vacation with my family for a beach holiday, more maths breakthroughs. They're very different. That was me on a beach on the south coast of WA in spring, and now I'm on the west coast of WA in autumn. Wildly different. The reason we've had so many maths breakthroughs at once is because Google DeepMind have just revealed that for over a year they've been working on something called Alpha Evolve, and it's able to come up with math solutions and math algorithms to find solutions, and they've released it all at once today while I'm on holiday. So I'm going to tell you more about the actual things they found, a little bit more about Alpha Evolve, and at the very end of the video I'll explain how I broke my arm. There is an area of maths called packing problems where you try to fit shapes into other shapes. I love it so much. And there's someone named Eric Friedman who runs the Packing Center website. Check it out. It's got all the state of the art, putting some shapes into other shapes as efficiently as possible. And yes, some of them look like a nightmare. I'm aware of all the memes of people being upset about how squares go into other squares. And I've been thinking about doing a video for a long time because I think it's fascinating, but some of them do make sense. So the current best way to put 13 hexagons in a bigger hexagon is this. And you go, okay, that makes sense. Hexagons packed neatly, that's going to be the optimal solution. But what's the best that humans know? The absolute optimal state of the art for putting 12 hexagons in a hexagon? Well, it's this. You just take one out. It's just the solution for 13, but then you remove one. We couldn't find any better than that. And you're thinking, well, Callum, there's a whole hexagon of extra space there. Surely we can do better. Well, Alpha Evolve has done better. So this solution, the big hexagon compared to the small ones, has a side length of exactly 4. Alpha Evolve found, and this is their diagram, this. So I'll link to the full press release below. They found this arrangement. Humans had never thought of this. Isn't that incredible? It brings the outer side length down from 4 all the way to 3.9419. Not a big saving, or not an important problem, but I'm still pretty excited. And while they were in there, they took the current best for 11, which is a lot more chaotic. That's got a side length of 3.943, and they brought it down to this arrangement, 3.930. These are all, I've taken images off Eric's website and the ones that they put in the Google DeepMind official paper. Again, linked below. Up next, circle and a square. This is where you can have different size circles, fit as many as you possibly can to a square. You add together all their radiuses to try and maximize that as big as possible. Here's the best humans had done for 26 circles, and here's the best they'd done for 32 circles. For those ones specifically, Alpha Evolve found better arrangements. They didn't put any pictures in their paper, so I knocked together some quick terrible Python code and visualize this one. That's their solution for 26. I want to check it works. It does. It's very nice. Now, not only does it have a bigger sum of all the radii, so if you add them up, this one's gone from 2.634 all the way up to 2.6358. Very small improvement. What I find interesting though is the previous one, found by humans, but probably with some computer assistance, is symmetric on the diagonal and only uses 9 different sized circles, whereas the one found by Alpha Evolve uses 26 different size circles. They're all unique. I really struggled to find, well, I randomly generated 26 different colors. Now, normally you use the same color for circles that are the same, but they're all different and they're not symmetric. So Alpha Evolve is finding different types of solutions to what humans were finding before, even though humans were previously using computers, but probably the way humans were coding it, we were still coding in efficiencies to make the search space easier or more efficient to go through, and we were still doing that in a human-y way, whereas Alpha Evolve wasn't. Oh, and the same thing applies for 32. 32 different circles. Isn't that nuts? I very quickly deal in the 11th dimension. There's a thing called a kissing number, which is the maximum number of spheres that can all touch, aka kiss a central sphere without intersecting with each other. So in 3D, if you got one orange, how many other oranges can touch it at the same time, you know, without bumping into each other? Is it 12? Is it 13? I'll leave it to you. You can look it up. I think Newton worked on it. But we try and solve this in higher dimensions as well. And some of them get easier because of the way they're combined, and others get more complicated. They decided to tackle 11 dimensions, complicated, and they found a whole new arrangement where you can fit 593 11-dimensional oranges all touching a central center orange. They may not be actual oranges. Now, I'm not going to try and visualize that. They didn't provide a picture either. My terrible Python code is not up to this. Here's the coordinates. There you are, check that out. Isn't that amazing? Just look at that and imagine it in 11 dimensions. It's pretty special. And there's a bunch of other findings in there as well. They put loads of different math problems through AlphaEvolve, and a lot of the time they just match the current state of the art because it may actually be fully optimal. And a bunch of the time they had new breakthroughs, new slightly better improvements they came across. So for example, if you want to arrange 16 points in 2D such that you minimize the ratio between the minimum distance between any 2 points and the maximum, have they got an improvement for you? Same with 14 points in 3D, and you can look through the whole paper yourself. But the main event, the headline finding, other than AlphaEvolve itself, was multiplication. They found a way to multiply 4x4 matrices more efficient than anyone else. Now, if you're the kind of person who's been watching this video and you're thinking, what is the practical application of any of this? Like, all my hexagons are already put away nice and neat. Well, multiplying matrices, this is where you need to care. So if you're sick of every time you got to multiply two 4x4 matrices together that have complex values, and in the process of doing all the columns multiplied by the rows, all that jazz, you're like, along the way, the absolute state of the art, discovered by someone named Strassen, Strassen's algorithm in 1969, still involves 49 scalar multiplications. I'm wasting my time. Good news, everyone. You can now do it in 48 scalar multiplications, which is an improvement, and no shade in all the other problems. This is something people care about. People care about multiplying matrices together because it's used a lot. Whenever you're doing something in a computer, you're probably multiplying a matrix in there somewhere. People were searching for this. No one could improve on it. AlphaEvolve has. In fact, here's the whole table of different size matrices being multiplied together, and AlphaEvolve either found a method that's equivalent to the current state of the art or improved on it slightly. So you can see the green ones are better. So for example, the first one, multiplying a 2x4 by a 4x5 matrix, has now gone from 33 scalar multiplications down to 32. That's a saving, and the rest of them. So how have Google DeepMind managed to get all these breakthroughs at once using AlphaEvolve? Well, it is, AI as such, but what they've actually done is, like a lot of us have realized, you can use large language models, for better or worse, to generate code. So if you want to come up with an algorithm, you could ask a large language model to do it, and it would do it badly, probably completely wrong. So then you're like, oh, this is awful, and you try and change what it's doing, and it's a nightmare. And they've realized they can automate that. So what they do is they take large language models that write code, they're using Google's Gemini models, and then they have AlphaEvolve as a system to send the prompts and data into the large language models, take the output, automatically test it against some kind of score metric for how well it's solving the problem. They have a big database where they very cleverly log all the output so far and what they did, so they're being efficient at how they're searching, I guess. And the AI, AlphaEvolve, is evolving the code using the large language model and testing it against what we want until eventually it gets better and better, and then becomes better than what humans have done so far. Sometimes, on a few problems. That's the graphic they gave me, by the way. And if you're thinking, why so much maths? I actually asked the people at DeepMind why they picked these problems for AlphaEvolve to solve.
Hi Matt, that's a great question. So we had some absolutely wonderful mathematical collaborators who were proposing problems to us, and of course they were focusing on problems where they thought that the best known constructions are maybe not quite optimal just yet. The only thing we really needed from each problem is that it comes with some kind of a score function that we can gradually improve so that we can measure our progress. Other than that, we're just trying to cover as many different areas of mathematics as possible. Now, for harder, more technical problems, it's not going to work quite as well, but that's okay because it can still be useful for you. What you can do is you can describe a couple different big picture ideas to different instances of AlphaEvolve. You hit run on each of them, you go on a holiday to Australia, and when you come back from the beach, you will see 3 different experiments running, and you can compare the scores of how well they did. So this can be a good way for mathematicians to compare various big picture ideas without having to work out all the details by themselves, by just outsourcing, delegating this working out the details to the tool. So these are just a couple of different ways you can use AlphaEvolve, and I'm sure there's still lots of low-hanging fruits in the area, and I'm just so excited to see what mathematicians will come up with in the next few years. But I'm going to stop here. I'll let you go back to the beach. Thanks, Matt, and sorry for disturbing your holiday.
It turns out math problems are just really good problems for this because the weakest part of the chain is that kind of verification step. It has to be a problem which can be easily verified, and that's what math is all about. Solutions that are often hard to find, but easy to verify. And so it makes sense they've just gone through and picked off a bunch of not low-hanging fruit, but they've gone through and found quirky, obscure math problems where you can either find a better solution out of the gate, or what AlphaEvolve's doing, find an algorithm that can then generate such a solution. And I imagine in the future they will get better at having that verification step work on bigger and bigger problems, which is not to say it hasn't helped already. Over about a year ago, they already started to use the output from AlphaEvolve to both improve Google data centers. That saved them, I think it's about 1% on their compute time across the servers, which, if you think about the scale of Google, that is a big number. They can do way more calculations for the same computation footprint, if you will. But also, you know what uses a lot of matrix multiplication? AI. So they've been using AlphaEvolve to come up with better algorithms for training AI, and even working on better designs for the custom chips that Google uses. So AlphaEvolve is also helping improve AlphaEvolve. Why is that making me so nervous? So what now? I don't know. I haven't planned this part of the video. Just want to stare at the horizon for a while. It's exciting and daunting at the same time. So here's the thing. This reminds me a lot of when computers first came online, and before that, to find prime numbers, we were doing it by hand. And then computers came around and we just had a spate of biggest primes all found very, very quickly because suddenly computers were good at that. Well, now computers are becoming good at something else. They've gone up a step. They're now able to come up with algorithms to find specific solutions to math problems. But I think it's going to be a similar situation. While some of these may be practical and useful in their own individual right, for the most part, they'll just be nice examples and things to help us as humans work on bigger mathematical understanding and proofs. We're definitely not taking the humans out of it, but I think it's interesting that now we've now got a bigger tap we can turn on. Instead of just doing raw, exhaustive searches, we can search for algorithms to do the searches for us, which I think, you know, as an owner-operator of terrible Python code industries, that might put me out of a job, but I like the fact we're going to find more fun bits of maths, and then as humans, we can play around with them and see what they reveal. And if you want to see more about how AI is actually influencing proving things and discovering theorems in mathematics, the incredible mathematician Terence Tao is thanked as one of the mathematicians who helped find problems for Google DeepMind to train AlphaEvolve on. So I think that's very interesting. And 2 days ago, I think, while I've been on holidays, Terry Tao started a YouTube channel and has put up a live stream of him converting something that was proven recently into Lean, which is not a coding language, but a way that we can start to get computers helping us proving things. It's super interesting. I'll link to that below, and you can go and check it out, and you can enjoy the brief window when I have more YouTube subscribers than Terence Tao. That's it. Thank you so much to Google DeepMind for letting me know this was coming out and giving me the embargoed paper, even though I was on holidays. That's fine. Thank you to everyone who watches these videos, supports me on Patreon, so I can just stop every holiday and release new maths videos. And it's nice to know we now have a new way to discover novel mathematics. It's me going on holidays, which is why I'm going to start a new crowdsourcing fund The Matt Parker Vacation Fund. You send me on holidays and inevitably new maths will happen. I mean, for the last 12 months it's happened twice with a 1-to-1. Like it's 100% correlation. Send me on holidays, we'll get more maths. Oh, I forgot to say what happened to my arm. I came off my bicycle and I broke the 4th metacarpal bone in my left hand, right down by the wrist. According to the medical practitioners, really nice break, real clean all the way across. There you go. I mean, I'd rather the null break, but they seemed impressed. If you want more details, I'll talk about it on my podcast, Problem Squared, in the next episode, which is out in like a week and a half. Short version, I'm a doofus.